Okay.
And we're back.
From my iPad.
Right.
Right,
I think
right.
fine. Yeah.
Okay. Okay, great. So thank you for the invitation and having me here. I would have preferred to come back to Moscow, but I guess that's for some other time. So what I will talk about in these 3 talks is based on work with Thomas Peternel on the one side and with Ji Liu and Feng Shao on the other side. Okay, so all of this is based on work. So it's independent projects, but you know, somehow there's a common theme to this Ji Liu and Feng Shao. Okay. So let me start with some general introduction. Why do we want to understand the cotangent bundle? So if you have X some projective manifold, then you're looking for natural objects defined on the manifold, which you can use to understand it and to study it. And of course, the most natural objects are going to be the cotangent and its dual, the tangent. Okay, so cotangent, omega x, and tx, its dual, the tangent bundle. Okay, so yeah, these are the most natural objects. And then somehow it turns out that studying vector bundles is kind of an issue, and this we will see this later on. So instead of this, because higher rank is difficult to start with, so you take the determinant and you get the canonical, and you take the determinant of the tangent bundle, and then you get the anticanonical bundle. Okay, so these are the most natural objects which you can attach to any projective manifold. Anticanonical bundle, canonical, anticanonical, depending on which one you like most. And now minimal model program is based on analyzing exactly these 2 line bundles. Okay, so minimal model program this, so MMP is based on the analysis of these 2 line bundles of the anticanonical. Okay, of the anticanonical, canonical or anticanonical divisor. And basically you want to decompose in 3 pieces. Want to decompose in 3 pieces. So you hope that in the end, somehow, after doing some operations, you will end up with 3 pieces where the canonical or the anticanonical behaves sufficiently nice. So you have the situation where minus kx is ample, you know, at least big, which then gives you what I would say is phonotype parts. Then you have the situation where kx is numerically trivial. Okay, so these are k-trivial varieties, and I will come back to this in a minute. And then there's the other part where kx is big, where you have everything related to general type. Okay, so so you want to split up your manifolds in these 3 types, and now this works rather well nowadays. And now once we have achieved this, what I would like to do is I would like to go back and say, now assume that I've learned already some things about the canonical divisor or the anticanonical divisor. Maybe with this extra information in mind, finally I could I say something about the cotangent bundle or the tangent bundle? Okay, and so I think this is a natural question, okay, because somehow when you take the determinant, you lose all kinds of information, but now you've put yourself in a situation where things are much better, okay? You have these kind of three typical geometries, and then you might think, how representative is this of the situation I started with, okay? So this is, of course, also what is behind these stability kind of questions Daniel has talked about. Okay, so, and now somehow the bad news is, or in general, knowing something about the canonical bundle will not tell you a lot about the cotangent bundle, okay? So observation, in general, the positivity of the canonical or the anticanonical does not say a lot about omega x, okay? Respectively tx, okay? Okay, that's the observation, and let me base this observation on an example. So example, let's look at the case where we have varieties, or projective manifolds with trivial canonical class, manifolds with kx numerically trivial. So these kind of manifolds, they come in three different flavors. So you have abelian varieties, so Cn mod lambda, and you have Calabi-Yau varieties, and then you have hyperkähler. Okay, so up to cover and products. This is the kind of varieties with a trivial canonical bundle which you will encounter. And so they all have trivial canonical bundle, or numerically trivial canonical bundle at least. And now you look at the cotangent bundle, and for the abelian variety omega x, it's a direct sum of O of x. Okay, so here you see everything goes well. The canonical bundle is trivial, and there's an easy explanation for this. It's because omega x itself is already trivial and sum of positive factors. Okay, so this is there you exactly get this relation. So this is nice. This is a good start. But then it turns out, if you look at these two other classes, then omega x does not behave well. Okay, so then you will not have any positivity or nice positivity of the cotangent bundle, and property is that omega x is not pseudo-effective. So I will explain what this means in like 10 minutes. Let me just say that this is not obvious. So I proved this with Thomas Peternell in 2017. Okay, so before this was known only in dimension 2 and 3, but this is known in all dimension. Okay, so omega x has all kinds of negative parts. Still, the determinant kx is trivial. Okay. So this is somehow the observation in general, going from the canonical to the cotangent bundle. This will not work. Okay, so this is one way of formulating it. Of course, you can formulate it also in a different way. You can say that if now I look at manifolds where omega x has some positivity properties, this might lead me to some very special and interesting geometry. Okay, so vice versa, if omega x is so pseudo-effective, and again, I will define this very soon. If this is pseudo-effective, I should expect some special geometry. Should expect some special geometry. Okay. Okay, and this is going to be somehow the main theme of these talks. I will assume that omega x or tx has some positivity property, and then I will show you how to exhibit some interesting global geometric features of the manifold. Okay, so this is the theme of these lectures. Assume omega x or tx is pseudo-effective, then deduce surprising geometric features. Okay, I think geometric features, and you will see. So this we would like to have properties which are much stronger than what usually happens when you have, say, some manifold with kx nef or so. Okay. Okay. Now, the way I plan these talks is that today I will just give you know, the definitions and some basic example for vector bundles, you know, positive vector bundles in some more abstract setting, and then in lectures 2 and 3. I will discuss examples for these themes. So, and I will talk about elliptic surfaces tomorrow, and then I will move on to, well, essentially del Pezzo surfaces in the third talk. Okay, so that we can really see by looking at concrete geometric examples what happens. Okay. Okay. Are there any questions for the basic basic setup? Oh, okay. So then let me give some definitions so that we know what we're talking about. Some definitions. Okay, so first, if you take X, some projective manifold, then you look at the Néron-Severi group of divisors. So NS of X, that's the Néron-Severi group of divisors, modulo, you know, numerical equivalence. Numerical equivalence. Okay, so this is a group, and now since I will want to take limits, I tensor this this Z module with R. Okay, and so then I get my vector space of R divisors mod numerical equivalence. Okay. Okay. So I have to work with R divisors to make nice definitions. But of course, in practice, everything I'm going to talk about is standard divisors. You know, define Z divisors. Okay. Now. So I have this vector space, and now let me recall when is a divisor big. So a divisor, and when I say divisor, I really mean element of the Néron-Severi group. D over X is big if I look at its asymptotic growth, it grows as fast as possible. Okay, so I look at the space of global sections, not only of D itself, but all its positive multiples. And this growth is then of the order L to the power of n, where n is the dimension of X. Okay, so being big means that up to take a multiple of your divisor, you will really get a lot of sections. And the standard example for this kind of situation is if you take A over X, some ample divisor, and you take also E, any effective divisor, then if you take the sum D to be A plus E, okay, so if you take something ample and you add something effective, then the sum has no reason to be ample anymore, but it's going to be big. Okay, this is big. Okay, so this gives you a standard example of what a big divisor is. And now, now that I've defined this class of divisors, let me mention following fact. If I look now at all the classes of big divisors in my vector space N1 of X, they generate an open cone. So this generates an open cone, which is called the big cone of the manifold X. And then I define Ceph of X to be the closure of this cone. Okay, Ceph of X, that's the closure of the big cone in my vector space. Okay, so I take this closure, and so there you see why we needed to tensor with R to make sense of this. So this is called the pseudo-effective cone. This is called the pseudo-effective cone, and a divisor is pseudo-effective, well, if it lies in this cone. Okay, if its class lies in this cone. Okay, so you have big divisors. These are the divisors which asymptotically really have a lot of sections, and then pseudo-effective divisors, which are obtained as the limit of these big divisors. And so that's a nice definition, but geometrically, you don't really know what this means. So fortunately, nowadays, we have this theorem of Buxom, Desmailly, Pound, Péternel, which tells us that a divisor D over X is pseudo-effective, and let me introduce the abbreviation Ceph, which is very much used nowadays. So a divisor is pseudo-effective if and only if, what's going on? If and only if the intersection numbers D intersected with C, this is non-negative for all the curves C and X. So not all the curves, you don't take arbitrary curves, but you just take those curves such that some multiples deforms in a covering family. Okay, so such that, say, multiple of C deforms in a covering family. Covering, or dominating family of X. Okay. Okay, so so what is the picture? The picture is that if you have your big manifold X, then in this big manifold you might have some bad curves, C bad, on which you have you have a negative intersection. But if you look at a curve C, which has the property that it's not alone, but you can deform it in your manifold in a family which eventually, will cover a Zariski open subset. If you look at these kind of curves, which are, curves which are not too special, then you will have a non-negative intersection. Okay, so if we deform sufficiently, then a negative intersection. Okay. And of course, this is very reasonable because this is exactly what happens if you take D to be an effective divisor. The effective divisor has non-negative intersection with almost everyone except maybe those people which are contained in the divisor itself. Okay, so this is a very nice, useful characterization. Okay, so this is the situation for line bundles or divisors. Now I want to move on to vector bundles. Okay, so now I use this to define positivity of vector bundles. And let me say there are many ways of defining positivity properties for vector bundles. You know, in particular, if you think about metric properties, there are lots of ways to do this. Here I'm doing the most straightforward algebraic way imaginable, and then I try to figure out what happens. Okay. So let V over X now a vector bundle of rank R at least 2. Okay. And now, in order to make my definition, I will consider the projectivization of this vector bundle. And I will always projectivize in the sense of Grothendieck. So projectivization in the sense of Grothendieck. So I look at hyperplanes. Okay, and now on this projectivization, I have my tautological bundle, which is denoted O of 1. Okay, you have this tautological bundle. And in order to simplify the notation, I will, in all these talks, zeta, that's going to be the first Chern class of this tautological bundle, okay? Because it's kind of a heavy notation, and since you will use it again and again, so I will look at zeta, the tautological divisor. Okay. Okay, so that's the construction, and now let me make my definition. So we say that the vector bundle V is big if my tautological class zeta is big. Okay, and so I can make this with big, and I will make the same definition for pseudo-effective. So the vector bundle is pseudo-effective if this divisor class is pseudo-effective. And of course, this mimics the more, classical definition that you say that a vector bundle is ample if this tautological class is ample, and then again taking limit and nef if this tautological class is nef. Okay, so this is the definition that we make. We just reduce the higher rank case to the case of a divisor, okay, which we think we've understood, okay, which we think we have understood. And let me give first an example, or rather an exercise where you can check if you understand what happens. So if X is P1, then my vector bundle is going to be a direct sum of line bundles, J equal 1 to R O P1 of A of J. Okay, so this is somehow the the easiest situation which you can have for a vector bundle. It's a direct sum. It's a direct sum of line bundles. And now I can characterize my positivity properties in terms of these line bundles. So we have the following thing. Okay, so the vector bundle is ample. Well, not surprisingly, this happens if and only if all these direct factors are ample, okay? And of course, this means that AG is at least 1 for all J between 1 and R. Now, the vector bundle is NEF if and only if the direct factors are NEF. So here we have AG at least 0, again, for all J between 1 and R. This is somehow the classical situation, which you certainly know. And now comes a more surprising situation. The vector bundle, it's big if and only if there exists at least one direct factor which is positive, so AJ at least 1, and your pseudo-effective if and only if there exists at least one factor which is well, pseudo-effective, and since we're on P1, this is this means AG at least 0. Okay, so you can try to do this as an exercise, and let me make an example. So as a somehow an example why to show you why looking at big or pseudo-effective vector bundles is somehow a bit more work than you might think when you read the definition. Let me go through one example in detail. And you will see we will encounter exactly this kind of situations in the next talks, okay? So here comes an example, and certainly this example contains a hint how to do the exercise. So I will look at a projective surface. If you have X, some projective surface, and I will take A over X, some very ample line bundle. And what I will use about this very ample line bundle is that, so it's space of global sections. So basically, you know, if M is high enough, this is going to be given just, you know, more or less by M squared times A squared over 2. Okay, so you have this. You're ample, so you know that the space of global sections grows with order M squared since you're on a surface, and the coefficient which tells you how fast you grow, that's exactly the self-intersection A squared over 2. Okay, so you take this very ample line bundle, and now I look at the following rank 2 vector bundle. I look at A plus A star. Okay, so I take this ample guy and I add to it some anti-ample guy. And well, I claim that this is big. This is a big vector bundle. Okay, so so this is an example, and so let me really carry out the example. Let me show you how this works. Okay, so I want to show that the vector bundle is big. So my definition tells me what to have to check. I have to take the tautological class and compute its space of global sections. Okay, so that's the definition. So let's try to do it this way. So we want to compute space of global sections of our tautological class, okay, for all powers L, so that we can see asymptotically how fast it grows. And of course, if you project you take the push forward of the tautological class to the power of L. If you push this forward onto X, then this gives you the L symmetric power of your vector bundle. Okay, and so we will try to compute the space of global sections of these symmetric powers. Now, let's do this. So SL of V, so that's the L symmetric power of A plus A star. So this decomposes also as a direct sum. So that's J from 0 to L. And then you have A, L minus G, tensor A star to the power of G. And J, and so this is, you can rewrite like this. You sum up, and then you have L minus 2J. Okay, so there you've decomposed your symmetric power in a sum of line bundles, and you observe that L minus 2J, that's non-negative if and only if J is at most L over 2. Okay, and why is this relevant? Well, because if it's negative, then certainly this direct summand will not give you any global sections. So in order to look at our global sections, I will just have to look at this part. So H0 X of the symmetric power, this is going to be a direct sum of J from 0 up to L over 2 of these line bundles. Okay. Okay, so now I have these vector bundles, these vector spaces of global sections of these line bundles, and the dimension of this vector space. So this is what we had up here. It's given by L minus 2J to the squared, and then you have the constant A squared over 2. Okay. So for each of these pieces, you know the dimension. And now if you want to know the dimension of this vector space, it's going to be approximately the sum L minus 2J squared times the constant A squared over 2. And I tried to do the exercise, and what I obtained was that this is L cube over 6 times A squared over 2. Okay, so what you see is that you get cubic growth. Okay, you have cubic growth for your space of global section, cubic growth. And this is very good because you start with a surface and then you projectivize this rank 2 vector bundle. So P of V has exactly dimension 3. Okay, cubic growth and the dimension P of V is equal to 3. Okay, so that's great. Indeed, our vector bundle is big. So we've checked that it satisfies the definition. And now comes the weird part. So as you know, typically we would like to have some relation between the properties of the vector bundle and its determinant. But certainly here, this doesn't start very well, because the determinant of V, that's trivial. Okay, so it's not big at all. Okay, so we would not get any useful hint by just looking at the determinant. Moreover, the idea of being big and of being pseudo-effective is that, well, there might be some bad loci, but basically, you know, so generically on most curves, you're non-negative. Okay, that's the idea of a pseudo-effective devices. Okay, so that's what I mentioned with the BDPP theorem. For most curves, things will be going well. Now here in this, this isn't really how it looks like here, because if you look at C in X, any curve, okay, any curve, if you look at the restriction of your vector bundle to this curve C, this is not NEF, okay? This is not NEF, simply because you will still have this anti-ample direct vector, so this is never going to be NEF, okay? And you can check this in the same way that you do the exercise on P1 before. Okay, so this is somehow counterintuitive to this feeling that pseudo-effective, or big even more, should tell you that on most curves things go well. Okay, now let's try to find a geometric explanation for these observations. Okay, so what happens geometrically? Okay, so what happens? Okay, so you have your surface X, and over the surface you have P of V, your threefold, which is a P1 bundle over your surface. Okay, you have this. And now in this threefold P of V, I have one section which is quite significant. So I will have here S0 in P of V. That's the section which corresponds to the quotient which I obtain by projecting onto a star. Okay, so that's the section corresponding to the quotient V maps to a star. Okay. Okay, so you have my rank 2 bundle. I have this rank 1 quotient, and such a rank 1 quotient defines me a section of my projectivized vector bundle, and this gives me here now some surface S0. Well, let's take color. Okay. So this is S0. It's a section, and I claim that this section will explain somehow why things are going so badly. So first observation is if we look at the restriction of the tautological class to this surface S0, then I get by construction of the tautological class, I get a star. So this is anti-ample. Okay, this is anti-ample. In particular, if I take, say, B in S0 any curve, then the tautological intersected with B, this is going to be strictly negative, okay? Because it's A star intersected with C, so this is then negative. Okay, so here you see why I think that this section is important, because certainly it contains many, many curves on which my tautological class, which I know is big, okay, I just computed that this tautological class is it's a big divisor, but here, if I look on what happens on S0, then it's not good, it's not good. There I get negative intersection numbers. On the other hand, for all the other curves B in P of V, which are not contained in the surface S0, one has that the intersection number is non-negative. Okay. And why is this? So just a hint of the proof. The divisor class of S0 can compute this. So this is the tautological minus the pullback of A. So vice versa, this tells you that the tautological, this is the divisor class of a 0 plus this pullback of an ample guy. And there you have it. You've presented the tautological class as the sum of something which is effective plus something which is nef. So you will have non-negative intersection numbers as soon as you take a curve which is not in a 0. Okay. Okay, so we've got this. We've got these two different kind of curves: those which live in a 0 and where I will have negative intersection numbers, and then all the others on which I'm not negative. Okay, so you see that if I look at it, so what's the difference between these 2 points of views? So here I was looking at curves. Here I'm looking at curves in X, and there the situation is strange, and I don't really understand what happens. Being big and having this kind of properties, this does not seem to fit together very well. Okay, so that's here I'm confused. And what did I do? Okay, so here I'm a bit confused. And on the other hand, if I look upstairs in the projectivization, there things behave as I want them to be. I have some bad locus. I have some bad locus as 0, where I have negative intersection numbers. And then in the rest of the varieties, I have non-negative intersection numbers. Okay. Okay, so summarize. So this divisor as 0, which I will call the bad divisor. This explains the negativity, the strange behavior of the vector bundle. Negativity of my vector bundle. And let me point out, so it's not an accident that this surface as 0 is a section. So somehow all these strange situations, they happen if you get bad loci which surject onto the base X. Okay, so somehow the main issue is that this map from S0 to X is surjective. Okay. Those are really the guys which give us trouble, when trying to understand these vector bundles, and this is what we'll see. Okay, so this is the example. Do you have questions for the example? Okay, so somehow my summary of this example is assuming that a vector bundle is big or pseudo-effective. Bundle is big, pseudo-effective. It's a rather weak. It's a priori. It's a rather weak property. Okay, all kind of funny stuff can happen. In particular, if you have negative loci which dominate X. Okay. In particular, if negative loci, and by negative loci I mean those loci on which I get from curves which have negative intersection with the tautological, if negative loci surject onto X. Okay, surject onto X. Okay, so that's the summary. On the other hand, I have the following hope, and this is what I will try to illustrate in the next lectures, is that if I take not an arbitrary vector bundle, but I take my vector bundle to be omega x or tx, the hope is that these bad loci, which make the analysis so difficult, they can actually contain some very interesting information about the geometry of X, okay? These bad loci, bad, negative loci contain some interesting information about the geometry of X. Okay, so what I will try to do in the next lectures is find, given a vector bundle in a certain, cotangent bundle in a certain, for a certain manifold, I will really try to find these negative loci and use them to learn more about my manifold. Okay, so this is what we'll try to do. And so I have some more time left, and therefore I would like to make a remark about, about sections, pseudoeffectivity and sections, existence of global sections for the cotangent bundle. Let's say for the cotangent bundle. Okay, so remark on existence of global sections. Okay, so if you have V over X, a vector bundle that is big, then if I look at the space of global sections, so I look at the space of global section of the symmetric powers, so that's the same as the space of global section for powers of my tautological class, and this is certainly non-zero for L sufficiently large. Okay, so if you're big, then certainly for some symmetric powers you'll have a lot of sections. If you assume that you're pseudo-effective, then this is false in general. Okay, so if V is pseudo-effective, then this is false in general. I mean, this is already false for rank equal 1, of course, then false in general, even for rank R equal 1. Okay, so in general, pseudo-effective does not mean that you're effective even if you go to some multiple. What you do know is the following. So pseudo-effective vector bundles. So if you want to write down what this property of being pseudo-effective means in terms of global sections, you have the following lemma, okay, which first appeared in a paper of Drell some time ago. So if you have H over X, some ample line bundle, then a vector bundle V over X is pseudo-effective if and only if for all C positive there exists I and G positive integers such that I is larger than C times J, and we have global sections, okay, and H0 of X of the isommetric power of the vector bundle tensorized with H to the power of J, this is not zero. Okay, so that's a characterization of being a pseudo-effective vector bundle in terms of global sections. So what is the idea? Okay, so being pseudo-effective does not mean that some symmetric powers has global sections. But now, of course, what you can try to do is you tensorize with this ample line bundle, and then you increase your chances of having global sections. And now the idea is that, okay, I know that I can do this, but of course somehow this is cheating because, well, if I tensorize with something sufficiently ample, everyone gets global sections. So this doesn't mean anything. But the trick is that here, since you assume that I is larger than Cj, so basically this means that I is much, much bigger than J, then somehow what you did is that you only added a very small piece of ampleness to your vector bundle and you get global section. Okay, so that's the idea behind this. And as you can see, this is awful. Okay, I mean this characterization, this is awful because it's very hard to check something like this in practice, and therefore somehow, although we know that in general being pseudo-effective does not tell you that you will have global sections even for symmetric powers, we would like to ask, maybe conjecture, that for the cotangent things are better. Okay, so question. Okay, I mean, this certainly would make life much nicer and easier. Question, conjecture, if omega x is pseudo-effective vector bundle, then do we have global sections for some symmetric powers? Okay, do we have? For some L in N. Okay. Okay. So this is the question, and of course, this is an analog to the well-known non-vanishing conjecture for the canonical bundle, to non-vanishing conjecture. Follows if you have X projective manifold that is not uniruled, and of course we know that the projective manifold is not uniruled if and only if Kx is pseudo-effective. Okay, so that's the assumption. Assume that you have this, then non-vanishing conjecture tells you that you will have global sections for mkx, or for some positive motto, okay, for some m in n. Okay. Okay, so we can hope, so far there's no counterexample, we can hope that something which is expected by many people for the canonical class, that something similar should hold also for the cotangent bundle, assuming that it's pseudo-effective. However, I should warn you that this non-vanishing conjecture for the cotangent bundle, it's not known even in situations which look very good. Okay, so warning, non-vanishing conjecture for omega x, not known, even if we assume much more, if we assume, say, omega x nef and its determinant kx ample. Okay, so even if I assume something which should make life much easier, this is not known. Okay, so it's definitely not known. it is known in some other special case. So conjecture is true. Conjecture is true if the canonical is numerically trivial. Okay, and so this is consequence. This is the consequence of this theorem, which I've proved with Thomas Peter. Now, if you look at manifolds where the canonical is trivial, if you assume that omega x is pseudo-effective, then you will have this non-vanishing property, simply because, as I told you at the start of this lecture, there is going to be some abelian part, and then the abelian part will give you one forms. Okay, so this is a direct consequence of this, and this might, of course, sound anecdotal, but somehow it tells you that although the non-vanishing conjecture for the canonical and the non-vanishing conjecture for omega x, they look similar, formally they look similar. If true, they will be true for very different reasons. So, I mean, non-vanishing for kx should be true because otherwise MMP doesn't work. Okay, so not so good. The reason why the non-vanishing conjecture for the cotangent might work is that the assumption of being pseudo-effective, of having omega x pseudo-effective, should lead to such special geometries that once you have understood the geometry, the existence of the global sections is a straightforward consequence. Okay, so this is the reason that this assumption that omega x is pseudo-effective, we do hope that this leads to a lot of restrictions and extra information about the manifold, which then later on will tell you that, of course, there should be global sections. Okay, and we're going to realize this strategy tomorrow for elliptic surfaces. Okay, so tomorrow we will see we will look at elliptic surfaces. And there we will get exactly this. For most elliptic surfaces, you will see will not have omega x pseudo-effective, but if it's pseudo-effective, then you will get the non-vanishing for free at the end. Okay, so elliptic surfaces tomorrow. Okay, so this is somehow on a positive side. Last warning. Certainly non-vanishing does not work if you do not just take omega x, but try to be a bit more general and take subsheaves or quotients. Okay, so it's definitely not true. Not true if we replace omega x. So we stay in a geometric setting, but we try to be a bit more general and look at subsheaves or quotients. Let's say probably quotients would be next reasonable guess. So there it does not work, and why not? We have this example, these examples of Hilbert modular surfaces. So these are surfaces of general type, and which have the property that omega x is a direct sum L1 plus L2. The canonical kx, so that's L1 times L2. This is ample in these cases. Okay, and so these direct vectors Li, they are Neff. Okay, so they're definitely pseudo-effective, very nice sheaves, but the Kodaira dimension is minus infinity. Okay, so you will never get global sections. Okay, so as soon as you move a little bit away from the cotangent bundle, do not hope to get any global sections, even for surface and rather special geometries. It's not going to be true. Okay, and I think this is everything for today. Thank you.
Thank you. Let's thank the speaker.
Any questions?
Out of curiosity, it's probably beyond the. So, what if instead of cotangent, you consider the tangent? Do you have any? I mean, sort of in the finite territory, right? So, do you have any?
Yes.
Uh-huh.
So we've studied that the tangent bundle, and I will talk a bit about this on Friday. And we looked at del Pezzo surfaces, del Pezzo threefold, and hypersurfaces in the projective space. And in all these three cases, we proved that Tx pseudo-effective implies that there is non-vanishing. Okay, so there things still work, at least in these examples. Nevertheless, I'm even more careful about the tangent bundle case than about the cotangent bundle case for the following reason. Even if you look at the anticanonical divisor, it is not known if, and maybe not so clear if anticanonical implies non-vanishing for the anticanonical.
All right,
Okay.
because this of MMP, which is not done at all, right?
Yes, so this is so on this side there is it's not done at all, and so far the examples that we found of manifolds with pseudo-effective tangent bundle, the geometry was quite special, and then somehow in the end it was obvious that we would have these sections. But right now, I think there are not enough examples to make it a conjecture.
I mean, there is this conjecture, which is of course wide open, but still, that if the tangent is well Neff, which is probably the same, then the thing is like a abelian variety times homogeneous space or something.
Yes, I agree. I agree, and somehow our interest in pseudo-effectivity is around this, and we try to develop this theme, and we try to come up with ways to produce sections, and if possible. So as you mentioned, this conjecture. So somehow this Campana-Pitana conjecture tells us not only will I get sections for symmetric powers of the tangent, but for the tangent bundle itself. And so what we try to do is give estimates for which symmetric powers you will get global sections. But I mean, we are now a bit further than the examples which we discussed in our paper, but not that much further. So it's really slow work.
That's of course a very hard question. Yeah.
Yes, yeah, I think so. Certainly for me.
Okay. Thank you. Other questions? Okay, so
okay. If not, let's thank speaker again.
Yeah.
And see you tomorrow.
Yeah. See you tomorrow. Bye.
Great. Thanks for the lecture for the lecture notes. Yeah. Okay. So see you tomorrow, everybody.